So last time we were talking about DC to DC buck converter, right? And we saw that a buck converter is, in a way, it's a combination of some switches which convert DC voltage into high frequency alternating voltage, and then there is a filter which filtered out the or rather removes the high frequency component and only filters out the average or the DC component, and thereby you get a output voltage which is a variable voltage which you can control using the duty cycle. So we also defined duty cycle, and we derived the expression or the relationship between the output voltage and the input voltage as a function of the duty cycle in a buck converter. We also saw how do you get the modulating signal or the switch on and off signal, right, by doing a comparison between a carrier, which is this triangular waveform, and a reference waveform, right. So the triangular waveform is also called as a carrier. Okay. We also saw that this is how the typical current would look like. So when the S1 is on, the inductor current would rise with it could rise with the different slopes depending on actual conditions, but if we assume ideal, all the components to be ideal and the output voltage ripple to be very small, right. So if we assume two things, small output voltage plus all the components to be ideal, in that case we see that the current waveform would be a triangular waveform, right. So it will be a straight line rising up, it will be a straight line coming down. Let's start with analyzing it bit further. Before that, I will introduce you to a sort of a quote unquote law which is called as a volt second balance or voltage second balance. What it means is that if you have an inductor, right, you can write its voltage VL is equals to L di by dt, right. And let us say this inductor is part of a bigger circuit, right. There are a lot of other elements which we are not seeing now in the screen, and the circuit is operating at sinusoidal steady state, right. Now we understand what is the sinusoidal steady state or the periodic steady state, right, which means f at x is equal to f at x plus capital T, right. This we already saw in the previous course, right. This is how we define the periodic steady state. If it's sinusoidal periodic, then we call it sinusoidal steady state, right. So this is, let us say, periodic steady state. So if you have this whole circuit, right, there could be a circuit here, there could be a circuit here. If the whole circuit, there could be a circuit here. So if all the circuit is at periodic steady state, and if you have an inductor, then you can use its equation. You can take VL into dt and is equal to L times di, and you can integrate on both sides, right. Let us say going from x to t equal to x to t equal to x plus capital T, and current would be IL at x to IL at x plus t. Is that okay? So I am basically integrating this equation over one period over which this has a periodic steady state. What would be the right hand side? It would be L times current at x plus t minus current at x. What would this be equal to? This would be 0 if you have steady state. Let me now, I would only use the word steady state, but you understand we are talking about periodic steady state. So this would be 0, and this means on the left side the integral of voltage, inductor voltage over a period of time Ts, right. So from, you can do 0 to Ts, you can do x to x plus Ts, anything. This average would be equal, or this integral would be equal to 0, right. This can also be written as, if you do it 1 by Ts on left side, 1 by Ts on right side, you can also write it as the average inductor voltage over Ts is equal to 0, right. It's the same thing. This relationship we call it as volt second balance, right, which is same as calling that average voltage across inductor will be equal to 0, or the integral of V dt, which is the volt second balance, is equal to 0. Ts is the period over which this circuit is periodically steady state. So for example, if it's let's say this circuit hypothetically has some 50 hertz sinusoidal, then Ts is corresponding to that 50 hertz, 1 by 50 hertz, right? Yes, in power circuits, in the buck converter or boost converters, it represents the switching period. Okay. So remember two things. This is the volt second balance. It's applicable if it's an ideal inductor, first of all, right? If there's a small r in it, that R plus L together will not follow this law. Only the pure L part of it will follow this law. That is one part of it. Second part is circuit has to be in sinusoidal or periodic steady state, right? That is very important. A circuit should be in steady state. If circuit is not in steady state, if you are during transient, then you cannot equate the average inductor voltage equal to 0. In steady state, you can do that. Any doubt? Any question? How many of you knew about this law before from the previous course? Okay, not many. Good. So today, after all, we learned something new. Now let's try to apply it to the circuit which we just saw, right? Which is the buck converter. We'll try to apply this law to buck converter. So first, let me just quickly, redraw the buck converter. S1, S2, RCL. This is direction of IL. This is polarity of BL. If this is S1 on and this is S1 off, then as we have done before, I can draw the inductor current starting from this point, going up, coming down, right? Of course, when S1 is off, then S2 is on, right? You understand that? When S1 is off, S2 is on, they are complementary, which we have already seen before. So the inductor current would rise, inductor current would fall. This is 0 dTs and this is Ts. What would be the relationship between IL at 0 and IL at Ts? What would be the relationship between these two values? The point at which current is starting, the point at which current is ending over a period of Ts. They'll be equal. Is that okay? They'll be equal only if circuit is in steady state. Okay. So we are assuming circuit as steady state. So for now, we can assume it to be equal. Now let's write let's draw the equivalent circuit of the top, bigger circuit for each of the case. So, or each of the zone, let's say, right. So the first period is period from time going from 0 to dTs, right, and the second period is time going from dTs to Ts, right. So the first period is this 1 and this is 2. So this is 1, this is 2. In the first period, if switch S1 is on and S2 is off, you can represent the same circuit like this, right, because S1 is on, S2 is off. So this is how the original circuit would transform to. And in the second period, when S1 is off and S2 is on, the circuit transforms to this one. right. So, any doubt so far, any confusion, any question? Okay, then next step what we do is we write the voltage across inductor in both the cases, which we have already done in a way, but let us still write it again. I am keeping the same reference polarity. So, in the left case, inductor voltage is equal to Vin minus Vo. In the right case, inductor voltage is equal to, how many of you say Vo? Raise your hand. How many of you say Vo? How many of you say minus Vo? Okay, and rest of you? All agree with minus Vo? Anyone who doesn't agree with minus Vo? Alright. Now, I can apply the volt second balance, which is integral of V dt from 0 to Ts is equal to 0, right. I know from 0 to dTs in period 1, during this first phase period, one second, during this first phase period 0 to dTs, you can see that the equation is VL is equal to Vin minus Vo. It remains same from 0 to dTs, and from dTs to Ts we have VL is equal to minus V naught. So, I am just going to substitute these two things in the integral. So, I can say I will split it into two integrals, right. The first one is from 0 to dTs, and in this VL is nothing but equal to Vin minus V naught into dt plus the second integral which goes from dTs to Ts, and the voltage is minus V naught into dt is equal to 0. So far so good. Okay, I will just rearrange the same integrals, and I can now write integral from 0 to dTs Vin times dt plus integral from 0 to Ts minus V naught times dt is equals to 0. Is the last step okay? What I have done is I have split the first integral into two, V naught and minus V naught component, and that minus V naught I tried to club with the third integral together. So, I have got only these two integrals, one from 0 to dTs and one from 0 to Ts. Now, what would the first integral be equal to? It will be equal to Vin times dTs. Is that okay? Is that fine? The first integral will be equal to Vin times dTs if Vin is constant, right. If Vin is constant, it is equal to that constant Vin multiplied by d into Ts, right. As far as again this course is concerned, ideal scenario Vin will be constant. The reality may not necessarily be very stiffly constant, it may still be fluctuating, but for all practical purpose as of now we assume Vin to be constant for all the circuits that we analyzed in this course, right. What about the second term now? What would that be? Minus V naught into Ts. Is the second term fine? Minus V naught into Ts. This is under the assumption that V naught. Okay, how many of you understand this? How many of you know this? Raise your hand. How many of you say V naught is constant? 1, 2, 3, 4, 5, 6, 7, 8. Okay, lot of people, right? Anyone with any other opinion? No other opinion? V naught need not be constant. What we are saying is, we are saying this capital V naught means the average output voltage. That's it. It may not be constant, right? What you are doing is integral from 0 to Ts V naught into dt. You divide it by Ts, multiplied with Ts. So what you have, that term is nothing but the average V naught. So what we are saying is V naught is nothing but the average value of output instantaneous voltage over a period of Ts. That's it. Need not necessarily be constant. It may be oscillating, it may have some ripple. In fact, it will have a ripple, right? Because you are doing on and off switching, output voltage will have a ripple. We did take a small ripple approximation, which is fine, but nevertheless it would have a ripple. So it need not be constant for this expression to be true. The input voltage has to be constant for this expression to be true, right? And that's it. Now I think you just rearrange and you will get output voltage is equals to input voltage into Ts. So the output average voltage is equal to input voltage multiplied by D. Yeah. Okay. Yes. V naught need not necessarily be constant. If output voltage is constant, fine. If it doesn't constant, that's also okay. Capital V naught symbol represents the average value of the output voltage. If it's constant, then average is equal to instantaneous all the time. If it's not constant, fine. So if you want to, let's say, visualize it, if this is your output voltage function, then this is your capital V naught and this is your small V naught as a function of time, right? So V naught, capital V naught is the average value of the output voltage. But again, since we are considering small ripple for now for this course, it's okay, it's safe to assume, both are one and the same. It's safe to assume that output voltage is almost constant. Any question, any doubt? Yeah. No, we are not. So what he is saying is, and rather what he is thinking is, in the last lecture, if you remember, we derived this expression V naught is equal to D times V in, right? So we are not starting from that V naught equal to D V in and we are again deriving it, no. But we are deriving it again by using a little bit different approach. Here we derived it, or rather here we derived it by using an approach that the filter is a low pass filter, right? That kind of approach. Here we have introduced a new way of analyzing things by using volt second balance, and now we are deriving it using the volt second balance. And this volt second balance approach is a more generic, so you would see that a lot of other circuits also you can analyze in the same way. Of course, the answer has to come out to be same because that's what it is, right? I mean, not necessary. We are assuming it to be steady state. It need not be steady state. Because we are turning on and off with a period of Ts and we are maintaining a duty cycle. So we are hoping that if you start today, by tomorrow something will be steady state. Yeah. So it doesn't get derived from the previous one. They are both, basic principle is the same. So you would get the same answer, of course, right? But the approach is a little bit different, and this is what is a more conventional approach, how you derive it, applicable to a lot of other circuits as we see forward. Okay, any other doubt? Alright, then our next step is, in analyzing this circuit, we have already find out the average voltage of the output and average voltage at the input. We have already found the relationship, right? Next step is, what is the inductor ripple current, right? And why is it important? What is inductor ripple current? Why is it important? So if you see the inductor current, right, it goes up, it comes down. What is the slope with which it is going up? What is the slope with which it is going up? So you imagine the equation V equal to L di by dt, right? The slope should be equal to V by L. So what is the positive slope equal to? V in minus V naught by L, right? And what is this slope? This slope is equal to minus V naught by L, right. So, there is straight line going up, straight line coming down with different slopes of course. Here you see that more or less slopes appears to be same, right, the way I have drawn it, you can imagine, right, the slope appears to be same. And why it looks so? Because if you see, I have actually placed dTs right in the middle of 0 and Ts, right. So, in a way, in this picture, duty cycle is almost equal to half, and if that is the case, then output voltage is half of input voltage, and if that is the case, the magnitude of the positive slope and the magnitude of the negative slope will be equal. So, that is why in this picture it appears to be equal, but in reality need not be the case, right. Let us just draw another one just to make sure. Let us say if this is Ts and this is dTs, this is how it would look like, right. Here this slope would be much more, this slope would be much smaller, and you can do the math. You assume d equal to 1 by 4 and go back and try to find out VO and then try to see the slopes. You would see the positive slope, which is V in minus VO, would now be much more than the negative slope, which is just minus VO. How many of you tried simulating something? I did ask you to do that. No one? Just few of you. Okay. Let me think if we can somehow give you a quiz on simulation. That's possible, but the only thing is that we have to think about it. So, I will think about it. Maybe we will discuss after this. I will discuss it in the TAs and we will figure out. So, you should go back, try to use some circuit simulator, right? Use your choice to observe all of these things, right? To observe all of these waveforms and so on. Okay, now coming back to the inductor current, right? If you see in this case, this vertical drop is what we define it as inductor current ripple, right? The vertical peak to peak value is the inductor current ripple. This is inductor current ripple. And how can we find the expression? We start with the same equation, V is equals to L di L by dt, VL dt is equal to L di L, right, and we integrate, and I understand that my current is minimum at 0 and current is maximum at dTs. So, I would take time going from 0 to time going up to dTs, where the inductor current is starting from IL min and going to IL max. Is that okay? The limits, I am not integrating now right from 0 to Ts. If I integrate over 0 to Ts, I will get back the same volt second balance of the average condition. Now, I am more interested in the ripple. So, what I have done is I have figured out where the current is minimum, where the current is maximum, and now I am integrating over that period, so that I get I max minus I min, right, I get the ripple component. Is that okay? So, if you have to find the ripple, you figure out where will be minimum, where will be maximum, and then try to integrate. So, on the left side from 0 to Ts, VL is equal to Vin minus VO. So, Vin minus VO, assuming that you assume that both of them do not have ripple just to make the life simple, and multiplied by dTs is equals to L times IL max minus IL min, which would transform to delta IL is equals to Vin minus VO into dTs upon L, which I can rewrite as 1 minus d times d into Vn into Ts upon L, right, because now I already know the relationship between Vin and VO. So, I have just substituted that relationship in that equation. Any question? Any doubt? Okay, so that is the expression for the ripple current. Now if I may ask you, what is the effect of inductance L on the ripple? If I increase the inductance, what will happen to the ripple? It will decrease, right? If I make it double, the ripple will become half. What is the effect of switching frequency? What is the effect of switching frequency on the ripple? If I increase the frequency, the ripple will be decreased. Is that okay? There is a switching frequency part in this expression, right? Which one is that? Ts. Ts is nothing but equal to 1 by Fs. So if I increase the frequency, that means I am reducing the time, that means I am reducing the ripple current. Alright. So let me just rewrite the expression. Delta IL is equals to 1 minus d times upon LFS into Vn, right? That's the right expression. So in this case, you can see that as L increases, ripple reduces. As switching frequency increases, ripple reduces. If I have to keep the same ripple for some reason, you can later on see what is the reason, but if I have to keep the same switching frequency ripple, if I have to keep the same ripple for some reason, and I want to reduce the inductance, right? What can I do? If for a given delta IL, how to reduce L? Why do you want to reduce L? Because the value of inductance determines the size of the inductor, right? What is the total energy stored in the inductor? Half Li square, right? So if you can reduce the L, you can reduce the size of the inductance, right? And therefore I want to reduce L. I want to make the converter as compact as possible. So if I have to do that, what should I do? I should increase Fs, right? This would lead me to increase Fs, but then, which I can do, but till what? 10 kilohertz, 100 kilohertz, 1 megahertz? Depends on the switch, depends on what they can switch at. And for a given switch also, you cannot just make it maximum value, because the losses, something called as switching losses, will become more. We have not gone into exactly what is switching loss, which we will probably do a little bit later, but the switching losses becomes more. So it's basically a trade-off. But yes, ideally, given an option, I would like to keep my switching frequencies very, very high, as high as possible. Sometime later, if time allows in this course, otherwise in some advanced course, you would learn what are the different types of losses and why they occur. Okay, what is the relationship between D and ripple current? Duty cycle and the ripple current? Yeah, maxima at half, right? So, delta IL max happen at D equal to 0.5, right? So if your duty cycle is very close to 0, or if your duty cycle becomes very close to 1, in either way your ripple current would absolute value will become 0. At D equal to 0.5, your ripple will be maximum. As per the expression, assuming the input voltage is fixed, inductance is fixed, Fs is fixed, right? Usually you won't be able to adjust duty cycle, right? Because your input is, let's say, 48, your output is 12. So your duty is already fixed. So although yes, it's good to see what is the trend with duty cycle, but it may not directly help you if the input and output voltages are fixed, right? D is already fixed. What you can choose is switching frequency and inductance. These are the only two things you can choose. Okay, any questions so far? Alright. Let's keep drawing some more waveforms. Let me draw the circuit here again for you. S1, S2, Vin, VO, IL, and now I am drawing this, showing two more currents. One is current going inside this, which is IC, and the other current which is going to the load, which is IR. Is this visible by the way? Too small? It's visible? Okay. So there's an IR, there's an IC, right? IC is the current component going in the capacitor, IR is the current component going in the resistor. In the previous case, we only have drawn till IL. We did not draw the individual output currents. Now we will try to even do that, right, as a next step. So this is TS, this is DTS, S1 on, S1 off. If I draw the inductor current, it goes from, goes from here to here, then it reduces from here to here. Okay. Now see the circuit. Inductor current waveform right, we have drawn. What would be this resistance current, IR? How would that look like? Would it look similar to IL? Would it look different from IL? How would it look like? How would IR look like? It looks similar to IL. Okay, next person. Constant. Next person. So all of you agree, right? IR would be constant because of our previous assumption that output voltage ripple is small. IR will be almost constant because IR is nothing but equal to VO upon R, and since we have assumed small output voltage ripple. ठीक है? Doubt है? Go ahead if you have any doubt. Good. So let me. So we know IR nature will be constant now. The question is, what will be the value of IR now? Right? It will be constant. It will be a flat line. Question is, where will it be? If I have to draw in the same scale as that of IL, if I have to draw IR, where will it be? Will it be below this triangle? Will it be above this triangle? Will it be somewhere in between this triangle? Where will it be? How do you find out? We use, or rather there is another law which is not very popularly used, but you can guess as soon as I write it. It's called as Ampere second law. Can you guess what this would be? Okay, let's ask the next person. Can you guess from the name Ampere second law? What would that mean? Next person. But where? Yeah, where? In current, there are switch current, there is source current, there is resistance current, there is inductor current, there is inductor current, there is resistance current, so many currents are there. So which current? You are correct. So ampere second law, as you can guess, it means the average of current is 0 or integral of I dt is equal to 0. But where? Next person? Next person? Person in front? Where do you think integral of I dt can be 0? Maybe capacitor, yeah, because the previous one happened for inductor, must be capacitor now. So I is equal to, IC is equal to C dVc by dt, right? You integrate from 0 to Ts, from capacitor voltage at 0 to capacitor voltage at Ts, assuming steady state, the right side integral will be equal to 0 and you will get the expression that average current in the capacitor is equal to 0 at steady state. Alright? Okay? So guys, remember superposition, right? If I look at, of course, can you apply superposition here first of all? Can you apply superposition here? Superposition? Yes? No? Okay, yeah. So, when switch is on, in from 0 to DTS, there is only one circuit, that is a linear circuit, you can apply it. From DTS to TS, again when the bottom switch is on, there is only one circuit you can apply. But you cannot apply superposition over both the periods because it is a non-linear circuit, right? So whenever switching is happening, diodes are there, switching is happening, it is a non-linear circuit. But then if I just zoom into right hand side and the left hand side circuit, I replace it with a voltage source V in, which is a squared wave, sorry, not this kind, which is a squared wave voltage source, right? So if I only look at the right hand side circuit, put a hand on the left side circuit and replace it with a square wave voltage source. Now can I apply, now is this a linear circuit, non-linear circuit first of all? What is the definition of linear and non-linear? How do you find out if the circuit is linear or non-linear? That is not the definition of a linear circuit. Okay, 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 yeah, right. So now if you see the right hand side circuit with a source, right? Source can be square wave, sine wave, DC, anything, right? The right hand side circuit is a linear circuit with a source. So I can apply superposition in the right hand side circuit, there is no problem, right? Only in the switching period I should not be applying superposition, but I can apply superposition in the right hand side circuit. So what I can say is, I can say, of course KCL is always applicable, so IL is nothing but equal to IC plus IR, this is always applicable, plus I can now if I try to apply superposition, right, what I can say is that IL has two components, right, one is the average component and one is the ripple component, right. Now this is superposition basically, I am splitting one current into two current. Since IR only has a DC component, it does not absorb any ripple current of the inductor. So complete ripple current of the inductor goes into the capacitor, okay. And because capacitor average current must be 0, therefore none of the average current goes to the capacitor, all the average current goes to the resistance, right. So from the inductor, you have two components of currents, one of them goes in the capacitor, other one goes in the output resistance. So the average component goes here and all the ripple component goes here. Is that okay? Right? Any doubt? Do you want me to explain this once again? Okay. Okay, let's So Kirchhoff's current law is valid, IL is equal to IC plus IR, that is part is fine. IL has two components, it has a ripple component and it has an average component. I can write it as a combination of two current sources, right. I can write it as a DC current plus a ripple component of the current. Is that part okay? So I am writing IL as a combination of average current, let's say 5 ampere, and a ripple current, a triangular of peak to peak 2 ampere, right. IR, we have just seen that IR will not have significant ripple current, it will be DC current only, right. And IC cannot have a DC current because of integral will be equal to 0. If you push a DC current, then integral will never be equal to 0, no? Is that okay? So IC can only have ripple, IR can only have DC value in this scenario. So the only matching possible is that the average component of the inductor goes into IR, the ripple component of the inductor goes into IC. Is that fine? Yes. Yes, ripple is IL max minus IL min, that's what we defined in the last slide, right? Okay, so that means now where should IR be in this picture? Let's come back to the question. It will actually be average of this, na? It will be exactly in the middle, right? It will be exactly in the middle. This would be your IR, exactly in the middle, because this is the average. This is IR magnitude is nothing but equal to IL min plus IL max. Yeah, my computer is quite a bit heated up now, divided by 2. Correct? So it's exactly in the middle. This is the average value, na? How would you find an average of a triangle? Max plus min by 2, right? Is that okay? Alright. Can you draw IC now? In the same figure. Why don't you guys go ahead, draw it in your notebook. Draw IC in the same figure. Okay, how would IC look like? Let's start from somewhere, na? Or koi kahan se start kare? Piche se. Go ahead. How would IC look like? Just explain, I'll draw it. It will be a triangle but below, right? So IC is nothing but Kirchhoff's current law, IL minus IR. So just apply the Kirchhoff's current law at each instant. Yeah, okay, this is IC. This is the axis, by the way, right? The green one is the axis. Let me draw it with the black color just to make sure that we don't confuse. This is the axis. Is that okay? Is this IC fine? Is this okay? Sure. What is the peak value of IC? Let's start again from the back. What is the peak value of IC? What is the expression in terms of the variables we have already defined? Peak value of IC. What is the symbol we have used for that? The closest symbol which we have used for that. What is the peak value of IC? Yeah, this we defined, this full, full thing we defined it as delta IL, right? And therefore, this peak value would be equal to delta IL by 2. Is that okay? Yeah. What will be the average of capacitor current? It will be 0, right? So the max value, which is delta L by 2, plus the min value, which is minus delta L by 2, both things if you add, you get 0, divided by 2, you still get 0, right? So the average value of this current is 0. Is that okay? Yeah, not constant, steady state at least. Yeah, if it's constant, perfectly fine, but even if it's not constant, it's steady state. So it's repeating itself after Ts, right? Yeah. Assuming it to be constant is definitely, you can show using that, but you can even show it even if it's not constant, but it's periodic, it's steady state, right? Yes. So he is saying if your source is a square wave, then all the currents and all the voltages at rest of the circuit should also be square wave, na? If I am calling this circuit to be linear, then he is saying, look, if your voltage source is a square wave, rest of the things should also be square wave. No, this circuit, let's say this circuit, forget about the buck converter, he is saying this circuit. If you say this circuit is linear, then if the source is a square wave, then every point you should have a square wave. Some, yeah, yeah. Mm. Mm. Yeah, so a square wave will not remain a square wave, that is not what linearity means. What we derived earlier in the previous course was, if the circuit is linear, the frequency of the source will be same as the frequency of rest of the variables. So if you have a square wave source of frequency Fs, your inductor current will also have frequency Fs, your capacitor will also have frequency Fs, yes, but then not necessarily the same shape. This is one way of looking at it. The other way of looking at it applies superposition, and I know it's bit of a catch because you feel it's not linear, so how can I apply superposition? But trust me, if you apply superposition, this is something which you have not done. Have you done Fourier series? All of you have done Fourier series, right? Good. So you can represent a square wave as a combination of sinusoidal signals of different frequencies, right? That's Fourier series. So you can say this is one source, this is two source, this is three source. You can go to n, right, but let's just say only 3, and now you have the same circuit, right. Now you apply superposition. In one case you will have only this one source of frequency Fs, other case you will have another source of frequency 2 Fs, third case you will have a frequency of 3 Fs, right, and then you can solve for it, and then you can add those components and you would get a triangle waveform essentially, right. So the frequency is the same because the circuit is linear. The shapes will change because there is inductor, capacitor, so they will different currents of different frequencies will flow. So they may add up and start looking weird, square, triangle, some other shapes, whatever, right? Okay, anyway, so yes, this circuit is linear very much. There is no question about it. So there is no problem what we were working on. Yeah, absolutely, absolutely, there is no question. Okay, let's come back, and I would request you to draw one more waveform, right? That would be the last waveform for today, and then we'll do the derivation. So just draw the last waveform for today. Draw the capacitor voltage Vc. In the same timeline, draw the capacitor voltage Vc. It's simple, right? Why are you getting confused? It's simple. How would it look like? How would Vc look like? Vc would look almost constant, right? Almost constant because we have considered ripple to be small, isn't it? We assume the ripple is small, na? So it will look almost constant. Is that okay? But I want you to draw the zoomed version of it, so that you can see that small ripple, right? So try to draw the zoomed version of Vc where you can see the small ripple, exaggerated version of Vc, right? Go ahead. And keep that in mind, I equal to C dV by dt. So you have I, you have to draw V, that's it. So if I use I equal to if I write this way, right, from this full thing is Ts period, right. So, this middle point will be dTs period. So, if the full period is Ts period, half of it is dTs, right. I am focusing on the capacitor current, the red waveform. The point at which this current is crossing here is equal to dTs by 2. Is that okay? Why? Because the negative value is minus delta I by 2 plus is delta I by 2, right, and this is a constant slope. So, therefore, it should cross the 0 at the midpoint of 0 to dTs, right. Similarly, this another point I can write it as d plus 1 times Ts by 2. So, I am just assigning all these 4 instances appropriate timing instants, right. Is that okay? So, midpoint is dTs of course, and the midpoint between 0 to dTs is dTs by 2, which is where the current is crossing 0, and then again current is crossing 0 at 1 plus d times Ts by 2. Now, between 0 to dTs, between this first period, what would be dV by dt? Would the dV by dt be positive or negative? How many of you say positive? What would be dV by dt? dV by dt is nothing but I equal to C dV by dt, right? So, dV by dt is I by C, whether I in the capacitor is it positive or negative from 0 to dTs by 2? Negative. So, dV by dt will be negative. So, if I am starting from here, it will go down, okay? Some shape, not straight line, of course, it is integral of a straight line, right? So, not straight line, in some shape it goes down. Is that fine? Okay. From second period, in the second period, what is the dV by dt? Is it positive or negative? It is positive. So, it will go up, okay. The third period, what will be dV by dt? Positive. So, it will further go up. The fourth period, what will be dV by dt? Negative. So, it will further come down. That is roughly how the voltage waveform would look like. These are of course not straight lines, these are integral of straight line. So, sort of they will be maybe more, will look little bit different, but that is fine. But roughly how this is how the ripple would look like. Is that part okay? Any doubt? Now, you tell me this, does it look same as what these guys have drawn or no? That is okay, don't worry about the shape of it, just okay, let me put it this way, just worry about where there is a minimum value, where there is a maximum value. Just look at that in this picture and what they have drawn. Is it same or not? No, right? Yeah, so don't copy this one then, use this one. Oh, is it? Yeah, I agree. Yeah, maybe you are right. Anyways, that's fine. Yeah, that's true. Very close by, I would say, very close. Maybe more or less correct. You didn't do the half of it, so you didn't point out at which instant it's maximum and minimum, but more or less correct, yeah. So, the minimum voltage happens at dTs by 2 and the maximum voltage happens at d plus 1 times Ts by 2, right. Why are we drawing this waveform? Why are we drawing this waveform? Anyone? In syllabus, you have to do it, yeah. Moreover, we are drawing it because we want to find the expression for the capacitor ripple, the same way we did the inductor ripple, right. So, to find the ripple, what you need is, you need the instant at which your variable will be lowest point and it will be at the highest point. Then you can integrate and you can find the ripple. Is that okay? So, therefore, we had to draw it approximately to figure out when is the minimum point, when is the maximum point. So, that now we can just do the integral the same way we did for inductor and we can find the ripple. Why we want to find the ripple is because we want to have small output ripple, then we can see how it depends on capacitance, inductor, frequency, duty cycle. We want to know all those relationships. Is that okay? Okay, I think with this let's stop today's lecture.